just spent some time looking at the concept of volume with integrals. Let's spend a little bit of time talking about density. And so in this video, the thing that we will be thinking about will be, well, assume that we have a thin rod of some kind. So I'll try to draw that nice and thin here. And it has length L. So let's say over here is where x is equal to 0. Over here is x is equal to capital L. And the information that will be given about this will be a density lambda of x. So this gives us the density at point x along the rod. So for example, if this is x is equal to 1 here, lambda of 1 will tell us how dense is our rod at that point. So we're given some length here for a rod, we're given a density function, and so the question is, what is the mass of the rod? Okay, so how do we go about tackling this? Well, let's not focus on the entire rod right away. Let's just think about a small little piece of, say, small piece of the rod. And let's say that, let's give three points here. X1 is the left end point, X2 is the right end point, and I'll kind of squeeze in there. X bar is the midpoint. Okay, so let's think about what's going on. What do we have here? We want a small piece. So the length of the piece, so that's going to be x2 minus x1. But really, we're going to take this to be really, really small, some kind of differential in the limit here. So we're going to think about this as dx. It's going to be an arbitrarily small number. And now, we also know, so we have this density here. Density could be varying, but we're going to approximate our density lambda as a constant, where that's going to be, lambda is going to be lambda of the midpoint over the entire piece. So the mass of the piece, mass of the small piece, is going to be the length times the density, where the length is going to be dx, and the density is going to be lambda of x bar. And maybe it'll be a little bit more convenient for us to switch the order there. It'll be a little bit more, look a little bit easier in our eyes to put that dx second. So the mass of the small piece is lambda at one of the points in here, the midpoint, times dx. So to go from the mass of the small piece to the overall mass of the rod, what do we have to do? We have to add up all the masses of every single small piece that we broke it into. But that sum of all those small pieces, we're thinking of them as infinitesimally small here, that sum becomes an integral. And so really what we're thinking about here, so we could call dm a little chunk of the mass here, the integral, so the overall mass, the integral of dm, is the integral where x runs from 0 to L of lambda x dx. So what does this tell us? It tells us that in order to, if we're given some density of a rod here, in order to find the overall mass of the rod, all we have to do is integrate. All we have to do is integrate our density from where x runs from 0 to L. So here, once again, just to remind us, we're in the section about setting up integrals. So here's our integral to work with density to find the overall mass of a rod. Let's do an example of this. So we want to find the total mass of a 2-meter rod of density rho, I guess I'm using rho here, of x is equal to 1 plus 2 times x minus x squared. And we can put all that in parentheses to say that the units there are going to be kilogram per meter, where x is the distance from one end of a rod. So m is going to be here the integral of a 2-meter rod. What we'll do here, we'll say one end is at 0, the other end is at 2. Integral from 0 to 2 of 1 plus 2x minus x squared dx. So this is the integral we have to do to find our answer. When we find the antiderivative of this, we get x plus x squared minus x cubed over 3. Plug in 0 and 2, and so that ends up as 2 plus 4 minus 8/3, and that is going to be 6 minus 8/3 is 10/3. There's other kinds of densities that we can do, not just rods. We'll look at that. We'll look at some more examples in the next video.